Okay, so we're going to look in that packet again at number 36. This is the Morse taper problem. Have you guys talked about the Morse tapers in the shop at all? No? They're basically standard tapers that are defined.
We know what it looks like and how it works.
Okay. Come on, get out of here.
Kind of calculations about it. How it's formed.
So what we're looking at here.
Spencer might be a little behind on this information, but why? You come in like that for it. 35.
36. So pretend that's not a horrible drawing of it. We have the width of the top of this opening here is given as 1.231 inches. I'm going to leave the inch marks off of it just for clarity right now. And this ball has a diameter of 1.2 inches. This is a number 4 Morse taper. The number 4 Morse taper is defined to be 0.62326 inches per foot of taper. So that's saying is in every foot, the diameter will reduce 0.62326. So at some point down here, this ball touches the sides of this tapered hole on each side. And of course, it forms a right angle on each side. Pretend I drew that evenly. Let me try that again, maybe. Like that. Now you can see that's not perfectly straight across. So what that means is the distance from here to here is going to be slightly less than the 1.2 inches of the diameter of the ball. Does that make sense? You look confused, Josh.
What did you say?
This red distance across here is going to be slightly less than the diameter of the ball.
Oh,
Yep. Because the diameter of the ball would go right through the center of it there. And we're going to be slightly below it. So what we're going to look at right now is this triangle. If I cut that in half, okay, what we know about this triangle is that this distance here is 0.6 inches. How do we know that? This is a radius of that ball. So half of 1.2 is 0.6. We also know, since this is perpendicular to this tapered surface here, that it is going to have a slope equal to the slope of that surface. So the question is, what is the aspect ratio of that surface? It is not 0.62326 to 12. Where did I get the 0.31163 from?
no idea.
0.62326 divided by 2. Why did I divide it by 2? Because this is the change in the diameter. So that means if I added up the change on both sides of the hole, it would add up to 0.62326. Each side separately is going to be half that.
How do you know that diameter is 6.62326?
It's not the diameter, that's the taper. That's the standard Morse taper.
The diameter of the taper, I mean.
Well, that's given as a Morse taper, and a taper is always changing diameter per foot. Since it's a number 4 Morse taper, that's what it has to be. Is 0.62326 per foot.
Where on the taper is that? Is it that length?
What that is saying is this is the same taper. All the diameter is changing at the same rate the whole way.
Yeah.
What that's saying is that if this is 1 foot long, the difference between this diameter and this diameter, big D minus little d, is going to be 0.62326 inches. So since we know that, we can turn that into a rate. It's that much per 12 inches, since it's 1 foot. But then half of that goes to each side. Half of that goes to each radius. That's why I divide it by 2. So that means, since this is perpendicular to that, this has an aspect ratio of 0.31163 to 12. How on earth do we equate that to this triangle? Good question. There's a little trick we can do with our aspect ratios. We can complete the right triangle. Now that this is a complete right triangle, how would I find the length of this side right here? A squared plus B squared equals C squared, right? So the square root of 12 squared plus 0.31163 squared.
How do you know that number is one of your sides of the triangle? When it's just a ratio.
It's not one of the sides of the triangle, but the sides of the triangle have to have that same ratio because that's the aspect ratio.
Right, so how can you just add that into your triangle equation like that?
Because the ratio of sides, the aspect ratio still forms a right triangle because the horizontal and vertical have to be perpendicular to each other. So it has to form a right triangle. Now this hypotenuse here doesn't exist to the aspect ratio. Yep. But this aspect ratio triangle does have to be similar to this big triangle. So if I call this side A and this side B, I know that the 0.6 relates to the 12.004 because those are both the hypotenuse, right? In the same way that A relates to the 12. A is horizontal, 12 is horizontal. So if I cross multiply and divide here, I'll find A. So I'm going to take 0.6 times 12 divided by 12.004, 0.5998. This is 0.5998 for A. I'm going to do the exact same thing to find B. 0.6 over 12.004 equals B over 0.31163. 0.6 times 0.31163 divided by 12.004. 0.015576. So I have those dimensions. What do they tell me? Remember, that was this little triangle right here. So that tells me quite a bit. What it tells me, first of all, is that the distance, oh crap, is that the distance across here, in other words, the diameter of that tapered hole where the ball is setting in it is twice A, 2 times A. So it's 1.1996. It's also telling me that that is located that far below the center of the ball. Does that make sense? What's that? Not a lick? Okay. Do you see where this triangle comes from? Okay. What we were doing is back here on the ball, right? The ball's sitting in the hole. We drew in a radius on the ball, right here. That has to form a right angle with the side of the hole, because it's a tapered hole. So then we drew this triangle here that describes how far down and over we go to get to that spot where it touches. The other way to think of it is we drew the radius in both directions, and since there's a slight angle to it, we made this big triangle, and we cut it in half. So what we're looking at here is just half of that bigger triangle. Does that make more sense? This is the 0.6 because that's the radius of the ball. The ball is given as a 1.2 diameter, so the radius is 0.6. And then we use the aspect ratio here to find that if this hypotenuse is 0.6, we find what the other two sides have to be. Because they have to be similar to that triangle. So now that we find that width there, what we're going to do is we're going to find how far it is from the top of that down to that point of tangency. Down to this point here where the ball touches the side of the hole. The way we're going to find that is we're going to use a taper. The top of the hole is 1.231 inches. That's given in the problem. What we just found is where the ball sits, 1.1996 inches. So we're going to use our taper formula.
But that's not going to the bottom of the ball.
Nope, that's not going to the bottom of the ball. That's going to this location on the ball.
Yeah,
So that's where the ball is sitting.
okay, because it is sitting there. Okay.
That's why we had to know this distance to figure out how far below the center line we are, the center of the ball. We'll come back to that. Once we figure out where this location is, we'll come back to figure out how far up we have to go to get to the top. So we're going to plug in our taper. 0.62326 equals big D of 1.231 minus little d of 1.1996 over, we're looking for L, so it's L over 12. Now, in my effort to solve this, I'm going to multiply by L over 12 on both sides. So cancel this out. This will be L over 12. This is L times 0.62326 over 12. I'm going to subtract over here. 1.231 minus 1.996. Clear. 1.1996. 0.0314. Now I'm going to multiply by 12 on both sides to get rid of this 12. So it's 0.3768. So I've got L times 0.62326 equals that. So now I divide by my 0.62326. So I get 0.6046, we're going to call that. So what we just found was the length of that taper that's required to get down to the diameter we needed. So from the top of this block down to where the ball touches the hole is 0.6046 inches. So now the question is, how far is it from there up to the top of the ball? Well, we know the radius is how much? 0.6. We know this little piece here is that. So we've got 0.6, 0.0. We're going to round this to 156. So this is 0.6156 inches from that spot up to the top of the ball. So the amount the ball is sticking up above the block is just the difference in those two dimensions, right? From that spot to the top of the block is this. From that spot to the top of the ball is this. So you subtract 0.6156 minus 0.6046 is 0.0110 inches. So now what we're asking for in the picture is dimension X, which goes from the very bottom. What's that?
0.5 something instead of 0.6.
Where?
Where you subtracted 0.6 minus 0.0155. 0.16. Yeah, how you get a bigger.
That's adding.
You're adding it?
Adding them.
How you
Yeah,
add it?
because this is 0.6 goes from here to here, then it's the 0.0155 or 156 to there.
Oh, okay, and
So
then
you got-
subtract it.
So then we're subtracting that from this, or this from that, actually. So we're trying to get from the bottom of the block all the way up. What we're given is for the height of the block itself is 4 1/8 inch. So 4 1/8 inch is 4.125 inches. We are going to add the 0.011 inches to that. So it's 4.136 inches. What do you think? Good stuff? Happy times?
That would be nice to do it on do another one on a separate piece of paper because I don't have room for my notes on this
Oh, sure.
little section.
If we get time, we'll try to go through another one.
Or is it going to test?
There will be one of those on a quiz.
Quiz
Yep.
or test?
Quiz.
Chocolate.
Not today, but maybe tomorrow.
Chocolate for a lot? Or what? Okay, hold on. Go bring it up a little bit so I can see.
That's the bottom of it.
Yeah, the bottom. The last.
Oh, the last part? That's the bottom of it.
So what was the final answer?
I should double check, make sure it is recording. Yes, it is. Okay, that's good. The final answer, X is 4.136 inches.
46?
Yep.
Okay.
Okay, now problems 44 and 45, I'm going to put out there as extra credit because those are two problems that are pretty difficult. So we're going to leave them out there for you to try for extra credit if you want to. Looking through 46 through 53 there, those are pretty standard, just drawing to scale factor problems. Any of those that you have questions on, I'd do one or two of those for you quick if you wanted me to.
Go 46.
46, okay. So number 46. In a drawing, we have 1 inch equals 1 foot. Well, it says 1 foot 0 inch.
Okay.
So now what that is 1 inch equals 12 inches. We have to convert it to a ratio. So we have to be looking at equal, same dimensions.
Good.
Once you've got that, then it's pretty easy. So then it's just a 1 to 12 ratio.
There's Reddit.
Okay. So then, since we're on that, we'll do number 47 here. A part that is drawn 2 3/4 inches. So we've got the 1 to 12 ratio. 2 3/4, does that go with the 1 or the 12? The 1. Because the 1 is the drawn. So you cross multiply and divide. 12 times 2 3/4 is 33. So it's going to be 33 inches in real life. Okay, jumping over to number 54 then. We've done these gear problems and we actually had the number of teeth. We can still do it with the gear ratios. So our gear ratio A to B is a 5 to 1 gear ratio. If gear A is turning at 1200 RPMs, how fast is gear B turning? Well, A is bigger. Does B have to be turning faster or slower? Faster. Smaller gears got to go faster. So this is an inverse relationship. When it's an inverse relationship, we do not use a proportion. We use the product. So gear A is represented by the 5. Its RPM is 1200. So 5 times 1200 equals, gear B is represented by the 1 times, we're looking for its RPM, so that's X. Notice we didn't actually have to have the number of teeth. We can just use the gear ratio in there. So 5 times 1200 is 6,000. 1x is just x, so we don't need to divide by the 1. So x is 6,000. That's 6,000 RPM. Number 55 is just another scale drawing. 51. That one you actually have to measure them out. So you've got to take a ruler and measure each length and then use that scale. So that's what you got to do with that one. So number 56. Pulley B turns 7 times for every turn of pulley A. Here we're not given the gear ratio, we're given the ratio of RPMs. Some put gear A as 1 RPM, or gear B or pulley B is 7 RPM. Do we think those are the actual RPM? No, they're not, but that's the proper ratio. 7 to 1. If A has a radius of 4, so that's 4 times 1, what is the radius of pulley B? So we'll call that X. Well, 4 times 1 is 4 equals X times 7 is 7X. Dividing by 7, 4 divided by 7 is 0.5714286 inches approximately. There's no radius. Any questions? I want to jump down to number 61. We got a discharge pump. A pump discharging 6 gallons per minute. Fills a tank in 30 hours. How long does it take a pump discharging 20 gallons per minute? So again, it's size times time here. We have 6 gallons per minute times 30 hours equals 20 gallons per minute times T hours. 6 times 30 is 180 plus 20T. Divide by 20. Time is 9 hours. So it'll only take 9 hours for the 20 gallon per minute pump to fill that tank. Which makes sense. Bigger pump should be less time, right? We've more than tripled the pump. We should more than cut the time to a third. Number 66. Anybody get an answer for number 66? Anybody get to number 66? Something seems a little off there. Let's take a look at what we got. So this is 9-inch radius. This here's a 4-inch radius. This is an 11.25-inch radius. This one is turning at 352 RPM. This one is turning at 2376. We want to know what that radius is on that last pulley. Actually, we want to know what the diameter is on that last pulley. We got to be careful. So, I can find the speed of the 4-inch pulley. How? Perfect. 9 times 352 equals 4 times x. So we're just going to do this. 9 times 352 divided by 4. $792. So 792 RPM is how fast the 4-inch pulley is turning. How do we find how fast the 11.25-inch pulley is turning? They are on a shaft. So they must turn the same RPM. That is 792 RPM. You remember that one from yesterday, huh? I usually catch through 3 or 4 times on that one before they start to see it. So that means I've got the 11.25-inch pulley times 792 equals whatever that radius is times 2376. So I'm going to divide by the 2376 here. So 792 times 11.25 divided by 2376 is 3.75. Is that my answer? No, that is a radius. I asked for the diameter, so we have to multiply by 2. It is 7.5 inches. Number 71. We have an alloy. In this alloy, there are 7 ounces of tin, 70 ounces of copper. We want the ratio of copper to tin. 70 to 7 or 10 to 1. That would be the tin to copper. Copper to tin would be 10 to 1. $69 mechanical advantage. So number 69, mechanical advantage is defined as the ratio of output force to input force. 20 pounds is applied to lift 60, so output to input. 20 pounds is applied, so that's the input force. You lift 60, that's the output force. So it's a 3 to 1 mechanical advantage. Number 73. We're going to lift with a lever here. We've got 280 newtons. That's just a unit of force. And we are going to push with a force of 35 newtons. If I want to know the ratio for part A of input force, or output force to input force, I'm lifting 280 newtons, that's my output, with an input force of 35 newtons. That's an 8 to 1 ratio. Part B, what is the ratio of distances? Well, what I'm lifting here only rose 4 centimeters. Well, I had to move here 32 centimeters. So the ratio of input distance is 32 centimeters to output distance is 4 centimeters is 8 to 1. What do you notice is the relationship between the ratios? They're the same ratio. When you use a lever, in fact, most simple machines, a pulley, a lever, a wedge, a corkscrew, you can lift stuff that's heavier than the force you put in. The trade-off is distance. Here, we're ignoring friction. You can lift a weight that's 8 times heavier than the force you apply to it. The trade-off is you have to move 8 times as far as what that weight's going to move. So if you want to lift it a foot, you've got to be able to move 8 feet. Same with a pulley system. If you've got a pulley system, let's say you've got a pulley system with a mechanical advantage of 3. So that means you're going to have at least 3 pulleys. These pulleys are going to have to be hooked. So we're lifting this weight here. It's attached. We can pull here and we can lift. What we pull here has to be 1/3 of this weight. So let's say this is a 300-pound weight. How much force do we have to pull with? 100 pounds. That's the 3 to 1 mechanical advantage. But let's say we need to lift this 5 feet. How far are we going to have to pull the rope? 15 feet. That's our trade-off. Now again, that's assuming no friction. We're assuming perfect pulleys. Some of that force is going to be lost in the pulleys. The distance won't change, but the force you have to apply is going to increase because you have to overcome the friction in the pulley. Yeah, rope stretch hopefully is negligible. 300 pounds it probably won't be, but depends on whether you have a good hemp rope or not. Next, I'm going to jump down to number 75. We're looking at an electrical circuit. So this is R1, which is 20 ohms. This is R2, which is 40 ohms. Voltage source of 120 volts. Part A, the ratio. R1, comparing the voltage drop, I should say. So we've got 40 volts across R1, 80 volts across R2. So the ratio of voltage drop R1 to R2 is 40 volts. 80 volts, it's a 1-to-2 ratio. Part B, the resistance ratio R1 to R2 is 20 ohms to 40 ohms, which is a 1-to-2 ratio. How are they related? They're the same. So the ratio of the voltage drops is equal to the ratio of the resistances. Number 76 is going to walk you through similar things. I'm going to leave that one as part of your homework. Number 86 is talking about converting temperatures. I want you to make sure you get to that one. What I want to go over in my last few minutes here is like 87 through 92. In fact, I'm going to do number 90. To be able to work with ratios, here we've got 2 pounds is to 3 gallons as X ounces is to 2 quarts. When we're dealing with a proportion like this, the unit that's here has to match one of 2. It either has to match that unit or it has to match that unit. One of the 2 have to match. Then whichever one it matches, the other 2 have to match. Well, there's no way I can turn pounds into gallons. Can I turn pounds into ounces? Yes. 2 pounds is 32 ounces. 16 ounces in a pound, so 2 times 16 is 32. So now those units are the same. That means these 2 have to be the same. 4 gallons in a quart, so 3 times 4 is 12 quarts. Very good. So this is now 32 ounces to 12 quarts equals X ounces to 2 quarts. You cross multiply. 32 times 2 is 64. Divided by 12 is 5 1/3. It's 5 1/3 ounces. Make sense? Okay. At this point, you guys should have everything you need to know to finish the packet. Which means tomorrow, very good chance there's a quiz on the packet.